Well, hello and welcome to Activity 23. We are on the first lesson, 23-1 of Activity 23, and we are going to learn about the law of sines. And so up until this point, we really just kind of defined a very simple definition of sine. It's a trig ratio. The sine of an angle, we'll call it theta or angle A or B or C or Z, really just some angle. The sine of some angle is the ratio of the opposite leg of that angle compared to the hypotenuse of that triangle. Hypotenuse. So that's a pretty simple definition of what sine is. It's a ratio based on a certain angle. And today we're going to learn about something called the law of sines. And we're going to, looking at our learning targets, we're going to prove the law of sines. We're going to start there so we know that it's true, see where it comes from, and then apply the law of sines. Once we know that something is true in geometry, we start using it. So for starters, today we're going to chunk items 1 and 2. So if you would just pause the video, read through our text, see where the start of the law of sines is, and then play through the video. Okay, hopefully you took a second to look at our opening text. So we're applying this to a pretty interesting idea, a real-world scenario here. The location of a spire spotted from 2 fire observation towers can be determined using the distance between the 2 towers and the angle measures. Remember that when we talk about these trig ratios, that's really what we're using. The angle measures, right, like sine of theta represents an angle measure, and the distances between the 2 towers, aka the distances of sides of triangles, that's what these two represent. So we're putting it back into the context of those ratios we've already learned about. And it tells us we've already solved right triangles. And really, we learned sine, cosine, and tangent to solve right triangles. Now, we're going to solve any triangle. Obviously, there are other triangles besides right triangles, namely the acute triangle and the obtuse triangle. In this lesson, we're going to learn how to solve those triangles as well. So for starters, let's go and make it clear that we don't know for sure if angle C was a right angle, but this diagram looks awfully a lot like what we saw in lesson 19, proving the Pythagorean theorem. So starting off, we were to draw an altitude CD from vertex C, and they even remind us what an altitude is. So you didn't have to get perfect here, but definitely want to make it look like CD is perpendicular to AB. And then they tell us to label the altitude with a lowercase h because we're going to write some ratios and we need to have some letter to represent the distance from C to D. So that's what h is. So now, just like in lesson 19, when we drew this segment, we created 2 right triangles. And they ask us, what are the 2 triangles formed? Well, triangle ACD and triangle CBD. Now, let's take a look at item 3 and 4. We're going to chunk those 2 together. So if you would, draw a line at the bottom of the page. So we're going to work all the way to the line on our own and then play through the video to see how we did. Okay, so for starters, we are dealing with right triangles. Recall that we just kind of added this auxiliary line here, CD, to make 2 right triangles just to prove that the law of sines is true. So we can write these trig ratios because now we do AC, this segment, which is labeled lowercase b, is acting as a hypotenuse because it's opposite of this right angle that was formed here because of the altitude. So for the sine of A, opposite of vertex A is now the side H. So we put H over the hypotenuse of this triangle, which is B. So the sine of A is H over B. Now remember, we're not saying that H stands for hypotenuse here, so just keep that in mind. They've just simply labeled this auxiliary line, the altitude that was added, they're just simply labeling that H. And then we get to write the ratio for the sine of B. So now looking at this triangle, this right triangle, opposite of vertex B is CD, which is labeled lowercase h, over the hypotenuse, which now CB, which is labeled lowercase a. That segment is the hypotenuse of this smaller right triangle. So the sine of b is equal to h over a. And I went ahead and added the definitions of cosine and tangent as well, just to kind of recall those to mind. So it says, now solve each equation from item 3 for h. So if you notice, these two equations, that's what they are because there's an equal sign between them. These two equations both contain that same segment h. And so we set each segment equal to h, or excuse me, each equation equal to h. And there's two ways to do it. Both are acceptable. On the first one, when I did sine of a equal to h over b, I wanted to keep that traditional right sine of a over 1 to make this a ratio over 1 so that I could make this proportion and cross multiply. H times 1 is h, and b times the sine of a is b times the sine of a. So the cross multiplying there got us h equals b times the sine of a. Now over here, some of you might have looked at it a little bit different and known, well, h is dividing by a, so if I multiply both sides by a, this will cancel out because the opposite of division is multiplication. And notice the a's will cancel out on this right side, leaving h, and a will be multiplying times the sine of b, very similar to what we just did on the previous equation. Then it said set the values for h equal. Notice both of these equations say that b times the sine of a is equal to h, and a times the sine of b is equal to h. So they equal the same thing, therefore we can set them equal to each other. That's called the transitive property, if we recall that. So two things that are equal to the same thing are equal to each other. So item B, we have b times the sine of a equal to a times the sine of b. And then C, it says complete the following statement, but I want to show you how we could complete that. So move this idea, this equation over here, b times the sine of a equal to a times sine of b. Well, if you notice, they got sine of a and sine of b essentially by themselves or written over some other value. So what I did on this left side was I divided it by b, and of course I have to do it to both sides, dividing both sides by b. And then on this right side, I decided I'd divide by a, so that it wouldn't be a times the sine of b, the a's would cancel out. So what happened was on this left side, the b's canceled out, and of course there would be a remaining in the denominator. And on the right side, the a's canceled out, leaving b in the denominator. So what we have just established is that the sine of angle A over the segment A is equal to the sine of angle B over the segment B. And I do want to point out something here, this math tip. In a triangle, the side opposite of angle A is labeled A, and the side of opposite of angle B is lowercase b. So what we're saying is the sine of an angle over its opposite side is equal to the sine of another angle over its opposite side. And notice we have just removed h from the equation because h was actually a value that we added to this diagram. So now, zooming back to the original diagram, we're saying that the sine of this angle, A, over this side, which is lowercase a, is equal to the sine of this angle over this side, lowercase b. Well, hopefully you can suggest that that would be the same thing for C as well, that the sine of C over lowercase c is equal to the two ratios we just mentioned. This is what is known as the law of sines. Let's take a look. In a similar way, you can show the sine of an angle over its opposite side is equal to the sine of another angle over its opposite side, and so forth and so on. So all of these ratios are actually equal to each other. And this is what's known as the law of sines. So we have just figured out, using the sine ratio from right triangles, we have used it now to find side lengths of other triangles. In fact, it says for any triangle, there we go, for any triangle ABC with side lengths A, B, and C, this is true. We just proved that this is true. Not sure why that just happened, but we'll clear that up. Now go back to the example at the start of this issue here, and the reason we had to figure out what the law of sines was. Fire spotters at stations located at A and B notice a fire at location C. So the fire is happening right here. What is the distance between station A and the fire? And so, because this is not necessarily a right triangle, we definitely don't know if it is. In fact, step one, they showed that it's not. We're going to use the law of sines. Notice opposite of angle C, they have labeled this side AB with lowercase c, and so forth and so on. So the first thing they ask us to do is find the measure of angle C, which we know any triangle, even if it's not a right triangle, the three angles of that triangle have to add equal 180. So they show that math here. 180 minus 42 from angle A minus 44 from angle B tells us that angle C is 94 degrees, which is actually good for us to understand that we're not solving a missing side of a right triangle. So we're trying to find the distance from that first tower at A to the fire at C. And I imagine the way this problem is set up is to see which fire spotter is actually closest to the fire. So we use the law of sines, and the reason we use the sine of B and the sine of C, granted we have all three angles, but we have the side opposite of C. You know, when building a proportion, you can only have one missing value. So we know now that angle C is 94 degrees, so we have the measure of angle C, we have its opposite side, which is 15, and our goal was to find lowercase b, so we definitely should use its opposite angle, which is 44 degrees. So we did the sine of B over B equal to the sine of C over C. We replaced capital B with its angle measure 44, capital C with its angle measure 94, and then lowercase c with its measure 15. They introduced something, if you've forgotten what it's called, the cross products property. Cross multiplication, we often refer to it. So they cross multiplied here. Sine of 94 times B is B times the sine of 94. And 15 times the sine of 44 is 15 times the sine of 44. So now they are going to divide, if this is B times the sine of 94, divide both sides by the sine of 94, and we get just B by itself. And then they actually used a graphing calculator to evaluate this ratio. So I'm going to show you how to do that. Recall to memory how to do that. So 15 times the sine of 44 over the sine of 94. So over on Desmos, I'm going to start by doing some parentheses just to make sure it does this multiplication first. So I believe it was 15 times the sine of 44. I'm going to close parentheses and put this all over the sine of 94, which, if I'm not mistaken, they tell us to round to the nearest tenth. And so we learned that the distance from tower A to the fire is 10.4 kilometers. So we have just used, and think about the heaviness of this. We just use the law of sines, the sine ratio, to help us find the missing side of an obtuse triangle, not a right triangle, which is actually quite fascinating. Now let's press on here that we've looked at the example from our the start of the problem. So now that we have an example under our belt, if you would draw a line here, try these A. We have a very similar scenario here, different measures, so keep that in mind. Try to find the missing measure before playing through the video. Okay, so before we dive into this, I want to say something, this important truth that we're really hanging our hat on for all of these last few lessons. Math is and will always be trying to solve something based on different information that's given. And so the reason, for example, the reason I chose this proportion above any other proportion is based on what's given. So let's talk about that. First thing we know is they tell us these two angle measures. So if you can, why not go and find this third angle measure? It possibly can help us out. In fact, it does. So again, these three angles had to add equal 180. So I took 180, subtracted 55, then subtracted 48, and 77 degrees was the remainder. Now, what I have in the law of sines is I have a complete ratio because I have the measure of angle C and the opposite side of angle C, which is, again, I went ahead and labeled it lowercase c. So I'm definitely going to use the sine of C over C. This is why you see that here, because I have that full ratio. I have the angle measure for C, and I have the side measure opposite of it. Then they asked us to find the distance between the boater located at point B, and notice they use capital B, so we're talking about this vertex here, and the lighthouse, which they told us was located at C. So now, if I'm finding the distance from B to C, I labeled this side lowercase a because it's opposite of vertex A. So I'm definitely going to use the sine of A over its opposite side because that's what we're looking for. So if you wondered, why did I use the sine of C over C and the sine of A over A? Well, sine of C, again, I had its angle measure and its opposite side. And I was looking for this side measure, and I had its opposite angle measure. So that's why I use these two ratios here. So I'm going to replace capital C with 77 degrees. That's what capital C is in our problem, over lowercase c, which is 1.5 kilometers. Then replace capital A with the measure of angle A, which is 48 degrees, over the side measure we're looking for, which is lowercase a. Now, I do my cross products just a little bit different. When I multiply A times the sine of 77, I just drop it down right below A. And then when I do 1.5 times sine of 48, I just drop it down right below 1.5. So I have 1.5 times the sine of 48 equal to A times the sine of 77. Remember, sine of 77 degrees is just a number. It's actually its own ratio in and of itself. So if this is A times the sine of 77, and I need to just solve for A, I'm going to divide both sides by the sine of 77. So like you see here, it cancels out or becomes the number 1. So A is equal to 1.5 times the sine of 48 degrees over the sine of 77 degrees. And notice I went ahead and put a little squiggly equal sign, which means approximate, because we are going to get a decimal here. In fact, they tell us to round to the nearest tenth. So I'm going to just show you again how to put that into Desmos. So we're going to do parentheses because we want to make sure it multiplies 1.5 times the sine of 48 first, divided by the sine of 77. And we get 1.14, which the 4 tells the 1 to stay where it is. Now, I want to show you what would happen. Now, Desmos might be a little tricky here, but I'll show you what happens if you don't do that division or those parentheses. I'm going to do 1.5 sine of 48 divided by, oh, well, that's nice, sine of 77. That actually works out. I know that in the TI-83 graphing calculators, if you don't use parentheses, there's potential for it to give you a false reading. So it seems on Desmos that we can use parentheses or not, which is nice for us. So the distance from B to C, or from this boater to the lighthouse, is 1.1 kilometers. So again, something pretty heavy here. We're using the sine ratio based on the law of sines to find missing sides of non-right triangles. So the last thing, because it's kind of a simple law, really, it's kind of a simple formula, we're going to complete the Check Your Understanding together before you move into the Lesson 23-1 practice. So we're going to chunk 5 and 6 together. So if you would, pause the video, complete 5 and 6 before playing through. Okay, so hopefully you took a second to think through these. Definitely love number 6. We'll explain more, but one of the greatest issues students have is understanding when and why we use these different methods to find missing sides of triangles, or right triangles, or in this case, what looks like an obtuse triangle, and how we can know which method to use. So that's what 6 really focuses on, but let's not jump ahead of ourselves. Number 5 says, show that the law of sines is true for a 45, 45, 90 triangle with the leg lengths of 1. So going back to our special right triangle, and I love that they're implying like, hey, the law of sines is true for any triangle, not just non-right triangles, but for right triangles as well. So if you recall, if we have a 45, 45, 90 triangle, the two acute angles are 45 degrees, and of course we have a right angle. So I drew triangle ABC such that capital C is our right angle vertex, and A and B are our 45-degree angles. So I went ahead and labeled the opposite side of A, lowercase a, the opposite side of vertex B, lowercase b, and the opposite side of capital C, the vertex C, lowercase c. And they tell us that the lengths of the legs are 1. So A is 1, B is 1. And we should already remember the special relationship that whatever the length of the leg is, the hypotenuse is that length times the square root of 2. In other words, 1 times the square root of 2. Or you could simply say it's the square root of 2, because 1 times any number in the world is that number. So we wanted just to prove that this is law of sines not just works for any triangle, but also a great way to remember this special relationship. So I did 2 proportions here, just showing that it is in fact true. So the sine of B over B equal to the sine of A over A. So I replace capital B with 45 degrees, lowercase b with 1. Replace capital A, angle A, with 45 degrees, and lowercase a with 1. And we don't have to cross multiply here. We see the exact same thing on both sides of the equal sign, which means this is true. Well, then you might be skeptical. Well, I was dealing with 2 45-degree angles. Of course it's going to be true. So I went ahead and wrote another proportion showing that the sine of C is also the sine of C over C is equal to the sine of A over A. And just remember, we've already proven that the sine of A over A is equal to the sine of B over B. So if I prove this true, transitive property says that all 3 ratios are equal to each other. So for the sine of C over C, I replaced angle C with 90 degrees. I'll add the degree symbol there, just so we remember that is what is being replaced. And lowercase c, which even though I've established it's the square root of 2, we're going to show that in fact it is the square root of 2. So I just left lowercase c there. And then I replace angle A with 45 degrees and lowercase a with 1. Cross multiply, we get c times the sine of 45 degrees. Let me add that degree symbol. And 1 times the sine of 90, which of course is sine of 90. Now this is c times the sine of 45 degrees, so we divide both sides by the sine of 45 degrees. And so c is equal to the sine of 90 over sine of 45, which is approximately 1.4. I'll show you I did that math on Desmos. So the sine of 90 degrees divided by the sine of 45 is 1.4. Well, you might be saying to yourself, well, that's not square root of 2. You told me that lowercase c in the special right triangle is the square root of 2. Well, let's evaluate what the square root of 2 is as a decimal, because we did just find a decimal form of lowercase c. So now going over to Desmos, I'm going to input the square root. Actually, I'm going to do this on another equation. Square root of 2. And notice it's the same thing we got in our previous ratio. The sine of 90 over the sine of 45 is equal to the square root of 2. So yes, the law of sines is true, not just for right triangle, but for the 45, 45, 90 triangle. Now let's look at item 6. Again, the whole point of this one was for us to understand when and why we use the law of sines. For starters, we can tell that angle Z is not a right angle. So law of sines should factor into our brain at some point, thinking, okay, it's not a right triangle, so we probably need to use the law of sines. Well, notice they want us to find ZX, which I went ahead and labeled ZX as lowercase y because it's opposite of vertex y. And I went ahead and labeled 12 as lowercase z because it's opposite of vertex z. And 7 as lowercase x because it's opposite of vertex x. So I started creating a proportion based on the law of sines. So I said the sine of y over lowercase y is equal to the sine of x over lowercase x. Pretty simple, right? Well, I know the measure of angle y, which is 35 degrees. Obviously, I don't know the measure of angle the measure of side y, or zx, because that's what we're looking for. And so in my other ratio, sine of x, I don't know the degree of x, which should already be throwing some red flags at you. But I did know that the measure of x, lowercase x, was 7. So here's the issue. We now have 2 missing variables in our proportion. And I'm not saying it's impossible, but it's near impossible to solve for 2 missing variables in the same equation. So can we use the law of sines to find zx? Based on what's given, unfortunately not. If we were given at least one other angle measure, if we knew just angle Z or just angle X, of course we could have found the third one because all three angles had to add equal 180. If we just knew one other angle measure, most certainly we could find the missing link from Z to X. So what we're really stressing here is on the law of sines, we need those angle measures. We definitely need those angle measures, and we definitely need one of the side measures as well. So that is the end of lesson 23-1, learning the law of sines. And hopefully we have a pretty good grasp of how to apply the law of sines. And if you need more assistance with that, be sure to tackle the lesson 23-1 practice below. Thank y'all for watching.